Welcome to my 61st tutoring session in A-level chemistry. In this video, I'll give a detailed explanation about 5 important parameters related to UV visible spectroscopy. The parameters are lambda max, bathochromic shift, hypsochromic shift, hypochromic effect, and hypochromic effect. So let me begin with the first parameter, that is lambda max. Let's try and understand the meaning of lambda max using this absorption curve with a plot of wavelength in nanometers on the x-axis and absorbance on the y-axis. What is lambda max? Now lambda max is the wavelength where you find maximum absorption of radiation by the drug molecule. Now peak of this absorption curve is the lambda max. It is the wavelength in nanometers where the absorption of radiation is maximum. Now here are some examples of compounds with their lambda max values. Benzene has a lambda max of 255 nanometers. Benzoic acid has a lambda max of 273 nanometers. And phenol has a lambda max of 287 nanometers. So each chemical compound has its own unique lambda max value. And therefore, the lambda max parameter can be employed for identification purpose, for the identification of the given compound. So qualitative analysis can be carried out using this parameter, that is lambda max. So lambda max is unique for each chemical substance, and therefore this parameter can be employed for carrying out qualitative analysis or identification of the given compound. Another unique feature of lambda max is that this parameter is independent of concentration of the substance. Now here's a figure which depicts the absorption curves of ergotamine tartrate at 5 different concentrations. And the lambda max of ergotamine tartrate is 578 nanometers, which is determined at different concentrations in tartaric acid solution using para-dimethylaminobenzylaldehyde as the reagent. Now when you observe the absorption curves carefully, you can find that at 5 different concentrations of ergotamine tartrate, you get 5 different absorbance values. But the lambda max of the drug ergotamine tartrate remains one and the same. That is, lambda max remains at 578 nanometers, even with varying concentrations. So this experiment clearly explains that lambda max is independent of concentration of the drug substance. So with increasing concentrations or with varying concentrations of ergotamine tartrate, there is only increase in the absorbance values, but the lambda max value remains one and the same. So there is no change in the lambda max value. And therefore, we can conclude that lambda max is independent of the concentration of the substance. So increase in concentration of ergotamine tartrate has no effect on the lambda max of drug. Now you will be making use of the same absorption curve in order to understand the rest of the 4 parameters, that is bathochromic shift, HYPSOCHROMIC shift, hyperchromic effect, and hypochromic effect. But this time you will be making use of the visible region whose wavelength ranges from 400 to 800 nanometers. We have already learned that lambda max is the wavelength where there is maximum absorption of radiation by the drug substance or the molecule of interest that is being analyzed. Now, what is bathochromic shift? Now, bathochromic shift, also called as red shift, is the shift in lambda max towards longer wavelength. So during bathochromic shift, you will find that there is shift in lambda max towards longer wavelength, that is towards the red region. So red region, you can see that the wavelength is more. So during bathochromic shift, there is shift in lambda max towards longer wavelength, that is towards the red region, and that is why this is also called as red shift, or this effect is also called as the red shift. Now there are several reasons for the bathochromic shift. I have highlighted the 3 important points here. So bathochromic shift is caused due to increase in conjugation or the increase in the number of double bonds with increase in alkylation and also due to presence of oxochrome. These 3 are the major reasons for the bathochromic shift or the red shift. Now these 3 points will be dealt in detail later on in the video. And what is hypsochromic shift? Shift in lambda max towards shorter wavelength is called hypsochromic shift. It's also called as blue shift. And hypsochromic shift, it is caused due to these 3 major reasons, and they are decrease in conjugation or double bonds, decrease in alkylation, and absence of oxochrome. Hypsochromic shift is also called as blue shift because, as you can see, during hypsochromic shift, there is shift in lambda max towards shorter wavelength, that is towards the blue region. That is why this effect is also called as the blue shift. So that is about the bathochromic shift and the hypsochromic shift. Now moving on to the rest of the 2 parameters, that is hypochromic effect and hypochromic effect. Now during hyperchromic effect, there is increase in the intensity of absorption. And what is hypochromic effect? During hypochromic effect, there is decrease in the intensity of absorption. Now here you need to note an important point is that in case of hyperchromic effect as well as hypochromic effect, the lambda max remains one and the same. Only the intensity of absorption either increases or decreases. If the intensity of absorption increases, it will be hypochromic effect. If the intensity of absorption decreases, it will be considered as a hypochromic effect. But the lambda max remains one and the same, as you can see from this absorption curve. While in case of bathochromic shift and hypsochromic shift, you can see that there is shift in lambda max either towards the longer wavelength or towards the shorter wavelength. So in case of hyperchromic and hypochromic effect, the lambda max remains one and the same, while in case of hypsochromic shift and bathochromic shift, the lambda max value changes. And how and why the lambda max value changes in case of bathochromic and hypsochromic shift, that will be discussed in detail later on in the video. Now one should familiarize themselves with these 2 key points. That is, the wavelength of the UV region ranges from 200 to 400 nanometers, and colorless compounds absorb radiation in the UV region. And the wavelength of the visible region ranges from 400 to 800 nanometers, and any colored substance will absorb radiation in this wavelength region. So one can differentiate a colorless compound to that of a colored compound in U-visible spectroscopy with respect to the absorption of radiation. A colorless compound absorbs radiation in the UV region, while a colored compound absorbs radiation in the visible region. So both colored compound as well as colorless compound absorb radiation. So only the wavelength of radiation changes or varies. So lambda max is the wavelength where there is maximum absorption of radiation, and bathochromic shift, also called as red shift, is the shift in lambda max towards longer wavelength. And bathochromic shift, as I've already mentioned, is caused due to increase in conjugation or double bonds, increase in alkylation, or presence of oxochrome. Let's discuss the first reason for the bathochromic shift, that is increase in conjugation. Now here's a table depicting a list of unsaturated compounds with their respective lambda max values. And let's see how the conjugation influences the lambda max of these 5 unsaturated compounds. In case of 1357 octatetraene, it has a lambda max of 300 nanometers. That is to say, this particular compound has maximum absorbance. That is, it has a maximum absorbance of radiation in this particular wavelength, that is at 300 nanometers. And when you observe the structure carefully, you can see that there are a total of 4 double bonds, and these 4 double bonds are alternately present. And this is what the conjugation means. So what is conjugation? Meaning of conjugation: alternative presence of single and double bond is called conjugation. The second compound is vitamin A1, which is also called as retinol. It has a lambda max value of 325 nanometers. So vitamin A1 or retinol has maximum absorbance of radiation at 325 nanometers. That is its lambda max. And it has a total of 5 double bonds. And they are in conjugation. And in case of vitamin A2, it has a maximum absorbance at wavelength of 351 nanometers with a total of 6 double bonds. And in case of beta carotene, it has a maximum absorbance at a wavelength of 453 nanometers with a total of 11 double bonds. While in case of lycopene, its lambda max value is 505 nanometers with a total of 13 double bonds. So what do you learn from these 5 representative unsaturated compounds? We learn that with increase in the number of double bonds, there is a corresponding increase in the lambda max values. That is, there is a bathochromic shift or red shift. So with the increase in the number of double bonds, we can see there is a shift in lambda max from 300 nanometers to 505 nanometers. Now continuing with the discussion on the effect of conjugation on the lambda max of unsaturated compounds. Now let's try and find out what happens when this conjugation in a particular compound is being disturbed or it is being altered or removed. Now ethylene has 1 double bond. Its lambda max value is 171 nanometers. 1,3-butadiene with 2 double bonds that are alternate to each other. It has a lambda max value of 223 nanometers. 1,3,5-hexatriene It shows maximum absorbance at 256 nanometers with a total of 3 double bonds that are in conjugation. And in case of 1357 octa tetraene, the lambda max is 300 nanometers. That is, this compound shows maximum absorbance at this particular wavelength. It has a total of 4 double bonds and they are alternately placed. So remember, conjugation is nothing but alternative presence of single and double bonds. Now, as you can see, with the increase in number of double bonds, there is corresponding increase in the lambda max values. Now, let's try and remove one of the double bonds in octa tetraene and see what happens. So, I removed one double bond from the conjugated octa tetraene and we see that the resultant compound is 137 octatriene. An interesting thing happens. The lambda max value falls from 300 nanometers to 217 nanometers. Why this happens? Because it is not only the removal of one double bond, but also there is loss of conjugation. So the symmetry is lost. The alternative arrangement of single and double bond is lost or it is being removed. So with the removal of conjugation, you can see the lambda max value falls from 300 nanometers to 217 nanometers. So this clearly explains the importance of conjugation. What happens when the conjugation is removed or it is being altered? Now from the absorbance values or the lambda max values of these 5 unsaturated compounds, we have learned that with increase in conjugation, there is shift in lambda max towards longer wavelength. That is, you see bathochromic shift. And with the removal of conjugation, there is fall or decrease in the lambda max value. So these 5 representative unsaturated compounds and their lambda max values explains the influence of conjugation on the lambda max of a compound. Now moving on to the next factor affecting the bathochromic shift, that is alkylation. Now this figure clearly explains the influence of alkylation on the lambda max of a compound. So with the increase in the number of alkyl and cycloalkyl groups, there is corresponding increase in the lambda max values. Now crotonaldehyde with one methyl group has a lambda max of 250 nanometers. Alpha enone with 3 methyl groups and one cycloalkane ring has a lambda max of 230 nanometers. While a steroid drug, progesterone, it has a lambda max value of 240 nanometers. When you observe the structure of progesterone, now progesterone is a steroidal drug. It has 4 cyclic rings or cycloalkane rings, that is 3 cyclohexane rings and 1 cyclopentane ring. So all the 4 rings are fused together, resulting in a steroidal skeleton, that is cyclopentanoparhydrophenanthrene. So here we not only see increase in the number of alkyl groups, but also the cycloalkyl groups. So with the increase in the number of alkyl groups on the cycloalkane rings, you can see that there is a corresponding increase in the lambda max values. So there is shift in lambda max towards longer wavelength with increase in number of alkyl groups and cycloalkanes in the parent structure. Now what about the last 2 parameters, that is hyperchromic effect and hypochromic effect? When do they happen? Now let's consider an example. Now phenylephrine, it shows bathochromic shift and hypochromic effect under basic conditions, and under acidic conditions they exhibit hypsochromic shift and hypochromic effect. Now under basic conditions, this particular drug, it has a lambda max value of 292 nanometers. So it exhibits bathochromic shift, that is shift in lambda max towards longer wavelength. And you can also see the intensity of the absorption increases. So under basic conditions, phenylephrine exhibits bathochromic shift as well as hypochromic effect. That is, you see a shift in lambda max towards longer wavelength, as well as the intensity of the absorption also increases. Now what happens when you record the absorption curve under acidic conditions? Now under acidic conditions, you can see that the lambda max value is decreased from 292 nanometers to 272 nanometers. And not only that, also the intensity of absorption is also decreased. So under acidic conditions, you can see that the lambda max value has shifted towards shorter wavelength, and also the intensity of absorption has decreased. So under basic conditions, you can see that phenylephrine drug exhibits bathochromic shift and hypochromic effect, and under acidic conditions, this drug exhibits hypsochromic shift and hypochromic effect. Now the influence of pH on the four important parameters, that is bathochromic shift, hypsochromic shift, hypochromic effect and hyperchromic effect, will be dealt in detail in my next video. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.